Welcome to the presentation of our paper, Evaluating Decision Makers over Selectively Labeled Data, a Causal Modeling Approach. I am Riku, Laine, and I have written this paper together with Antti Hyttinen and Mathioudakis, and we are all from the University of Helsinki. Let's begin with a case example on bail violations. Bail is a lump sum of money which the defendants pay as a promise to attend trial and honor other conditions. The decision whether to grant bail or not is made by the judge after a meeting with the defendant. After the meeting, the judge makes a risk assessment of the defendant, whether they will pose high risk of violating the bail. Bail is then granted to those who are of low risk of violating the conditions. Now, we wish to replace the judge with a machine. The machine replaces the judge as an independent decision maker, making its independent decisions on who to grant bail and who to jail. Now we are tasked with the mission to evaluate the performance of the machine. Evaluation of machine decision makers is based on historical data with odd decisions and odd outcomes. The historical data might not contain external information which was used in the making of the decisions, such as behavior of the defendants in the room of court. Some of the odd decisions might additionally prevent us from evaluating alternative decisions, such as in cases where the machine decides to bail someone who the judge had originally jailed. Evaluation in those cases is not possible as the data does not exist. We call the data in these situations selectively labeled. Selective labeling is a process where decisions prevent us from observing some of the outcomes. If we were to use only cases with outcomes available, it would induce selection bias, as we would not have the risky people in the data at all. It prevents straightforward evaluation whenever the machine and the judge disagree, whenever the machine decides to bail a case when the judge had originally decided to jail. Our task is then to evaluate the machines while accounting for both this selective labeling and unobserved information which might have affected the decisions and the outcomes. In our approach, we infer parameters of a Bayesian model the data generating process, and using the model, we impute the missing outcomes. We use this imputed dataset to evaluate the machine decision makers. The result is less bias and less variation in our evaluation than the state-of-the-art algorithm. Our setting does not only consider bail violations. Selective labeling is also encountered in lending, medicine, and insurance. In lending, you have clerks who wish to give loans to good borrowers. In medicine, you have doctors who wish to prescribe procedures to patients who are most likely to benefit from them. In insurance, low-risk customers are preferred for increased revenue. In all of these situations, evaluating decision makers before they are deployed is critical. That's why great care should be taken when evaluating decision makers over selectively labeled data. This is the outline of our presentation. Next, I will present our setting and the objective of our research. Then we will discuss the central components of our approach and finally present our experiments and their results. Our setting consists of 5 different variables shown here. The variable J indexes the different decision makers, telling us whether Judge Bernard or Judge Abby made the decision. Variables X and Z might be uni or multidimensional. Here we use only binary outcome Y, but of course the setting is expandable to accommodate continuous Y, such as in case of the insurance where the outcome would be the revenue. Let's next go through the data generating process step by step. First, a case is assigned to a judge. The judge makes a binary decision T based on all information. The decision is based on predicted risk of the case. If the case has low risk for an unsuccessful outcome, we are more likely to give a positive decision. If we give a positive decision, we may observe either a successful or an unsuccessful outcome. This of course corresponds in the bail case that if we give bail, we either can observe a bail violation, which is an unsuccessful outcome, or no bail violation, which is naturally a successful outcome. If we give a negative decision, a jail decision, we of course cannot observe bail violation. This process results in the dataset D, which does not contain information on the unobserved features Z. To evaluate the machine decision makers, we of course need to define them. The machines are defined using dataset D, using which we build a decision maker M, which makes a separate independent binary decision T based on only features X. That means that the machine cannot observe, for example, behavior of the defendant in court, as expected. We define two measures, failure rate and acceptance rate. Failure rate is subject to acceptance rate in that if we increase acceptance rate, the failure rate usually increases too. The overall objective is not to have a failure rate of 0, as that can simply be achieved by setting the acceptance rate to 0. In the bail or jail example, this corresponds to not observing any bail violations if we do not give any bail. Our objective is rather the objective of evaluation. Given a dataset D, we wish to estimate the failure rate of any machine decision maker M at any level of acceptance rate, as accurately and as precisely as possible. The fundamental problem in evaluation is evaluating in cases where the machine and the judge disagree. We can of course consider of discarding the cases whenever the judge has decided to jail the cases. But of course that would induce selection bias, as the risky people would be missing. To avoid this problem in our evaluation, we compute counterfactuals, which tell us what would have happened if the judge had decided to give bail. Intuitively, we compare cases with similar features X. Of those cases, one was jailed and the others were released on bail, which resulted in no bail violations. Now we are asking what would have happened if the jail decision would have been flipped. Given a precise judge, the outcome would more likely be negative than based on X alone because of unfavorable unrecorded information. In the bail or jail example, this would correspond to that the case would behave aggressively or unremorsefully in the meeting with the judge, and then the judge would infer that the case would more likely to violate the bail based on their aggressiveness. To compute the counterfactuals, we use Perl's three-step protocol. The underlying causal model is defined as a hierarchical Bayesian model. Using the model and its posterior for its parameters, the counterfactual y can be computed within the equation. In practice, we use the MC-MC functionality of Stan. We use the computed counterfactual whenever the true outcome is not available, that is, whenever a case was jailed. We use the observed outcome with bailed cases. Our failure rate estimate is then a sum using only cases with positive decisions from the machine decision maker. We call this approach counterfactual-based imputation, or CFBI. In our experiments, we use two different kinds of datasets, a synthetic dataset and the compass dataset. The synthetic dataset contained randomly generated cases with randomly generated features. The decision makers were assigned with leniencies ranging from 0.1 to 0.9, so that the decision makers released somewhere between 10 to 90% of cases assigned to them. If the decision they gave was positive, we drew the outcome y from a Bernoulli distribution. The compass dataset is a real dataset from the United States of America, which contained demographics and risk scores computed with compass for roughly 6,000 people. Compass is a set of tools assisting decision-making in the criminal justice system. The machines employed the demographics in their decision-making. The outcomes were available for all defendants, so we employed synthetic decision-makers. The judges jailed cases based on the compass scores indicating high risk. The unobserved information would then be encoded in the compass scores as it is derived from many more factors. The outcome was recidivism in the following 2 years. To hand out the decisions, we deployed 3 different decision-making algorithms: batch, random, and independent. Batch sorts the subjects based on risk and releases the top portion. Random hands out decisions randomly, and independent is a threshold-based approach. All of these algorithms are feature independent so that they don't depend only on observed or observed and unobserved features, so we use them both as judges in the data and as the machine decision makers. We deployed 4 different evaluation algorithms along with CFBI. True evaluation is the baseline against which we compared. It uses the true outcomes of all cases, meaning that whenever a case was jailed, true evaluation sees what would have happened had the case been given bail. Labeled outcomes disregards the jailed cases. Logistic regression imputes the outcomes for jailed cases. Contraction is the state-of-the-art algorithm presented by Lakkarayu et al. A few years ago. It is tailored for this kind of situation and uses a subset of the data. It assumes that we are jailing the cases who the most lenient decision maker jailed. It sorts the other cases by the lowest leniency where they are bailed by the machine, so that the top of the list are the least dangerous cases. Next, we additionally jail or contract the subject at the end of the list to match the evaluation leniency. Then, the failure rate estimate is a result of a division. Here are the results using synthetic data. The goal is to be close to the green dotted line for true evaluation. We see here how the labeled outcome estimates the performance of the machine better than it actually is. Contraction and CFBI are both very close to the truth, CFBI with less variation. Next, we also experimented with restricting the maximum leniency of the decision makers in the data. The result here is seen on the left, and the goal is the same, to be close to the green dotted line. We see here how the contraction is limited by the maximum leniency in the data, whereas CFBI is not. And again, CFBI has the best performance of the evaluation algorithms. On the right, we experimented with different combinations of decision-making algorithms. The goal here is to be as close as possible to 0, or as low as possible. We see here that CFBI offers stable performance, whereas contraction has a variable performance. Here are the results using compass data. The goal here is the same, to be as close as 0 to possible. The figure explicates how the performance of contraction is critically reliant on how many cases are assigned to the most lenient judge. The performance of CFBI is stable in all cases. To conclude our findings, selective labeling must be considered when the missingness of the outcomes is dependent on the outcome. Additionally, we presented an approach, CFBI, which evaluates decision makers using counterfactuals. Counterfactuals are used by considering and computing what would have happened if alternative decisions were followed. This results in all-round better evaluation, even in situations where it wasn't previously possible. There are some future work proposals. We would like to include correlations or more causal dependencies between some of the variables. Most notably, we would like to include a dependency between J and X, meaning that some of the judges might be specialized to some type of crime. Also, we would like to use CFBI as a machine decision maker or enhanced learning using the algorithm. Of course, the minor addition would be to expand CFBI to accommodate non-binary outcomes. Thank you for listening.